It is such an honor to be here tonight, and I'm so pleased to see you all turning out interested in what NASA's trying to do, though I want to make it clear from the beginning that the story Jim and I are going to be telling you while we're telling you NASA's perspective on it, this is not NASA's path, this is not NASA's plan alone. The spacefaring nations of the world have gotten together and put together a global exploration roadmap. What do the spacefaring nations of the world want to do next in human exploration? And that's what we're going to be talking about tonight. But this truly is an international endeavor. It is not something any one nation can do on their own. It's something that humanity is going to do together, and I think that makes it even more exciting. Now, I'm going to step back for a minute and just remind you of the science that we do all together at NASA. And of course, that science literally spans the universe. From the science that we do trying to understand our own sun, its behavior, why do we get these giant solar flares and coronal mass ejections, how does the complex interior of the sun work? And obviously, we then want to understand, once you have a solar flare or coronal mass ejection occurring, you're getting this massive rush of energetic particles towards the Earth. And that can have an effect on astronauts, but even more importantly, goodness gracious, it could affect our cell phones. So understanding the behavior of the sun is something that we're certainly keenly interested in from a scientific perspective and from a practical perspective. We do a lot at NASA studying the universe, the origins of the universe, the nature of stars, the birth of stars, the nature of galaxies, why are there black holes at the centers of so many galaxies? The questions about the universe, its basic nature, the nature of dark matter are endless, and NASA has a number of assets really taking every part of the electromagnetic spectrum to look deep into the universe, further back in time to understand these processes. We do an amazing amount of work on the International Space Station with our partners every day to try to understand the science that you can get out of microgravity research. And I'm going to be talking about that in a bit in terms of the long-term effects of microgravity on the human body. Lots of things don't go so well in microgravity, and that we need to get past that because it takes about 8 months to get to Mars. So we need to get humans to Mars healthy by the time they get there, and we're utilizing the International Space Station to get ready for that. Most of you are familiar with all of the work we do here in our own solar system, again, with our international partners. We have spacecraft right now, all the way from Mercury, the Messenger spacecraft at Mercury, to the Juno spacecraft on its way to Jupiter, to the New Horizons spacecraft, which is on its way to Pluto, trying to put our own planet Earth into the perspective of all the planets in our solar system. And we have 17 spacecraft around Earth. We do not forget to look homeward at our own planet, trying to characterize our changing climate. The climate is changing so rapidly, it's changing differently in different parts of the globe, it's changing weather patterns, and NASA has a huge number of assets looking at everything from every aspect of the water cycle to the amount of carbon in the atmosphere. We're going to launch a spacecraft later this year to be measuring atmospheric carbon dioxide, to all the work we do looking at gravity, which helps us understand when we draw too much water out of an aquifer and the ground actually starts to sink. So all the aspects of our changing climate we're very focused on at NASA. When you look at the basic questions that drive across all of those disciplines that I just talked about, really you can find in all of our guiding documents these questions, and you might say, well, those are kind of simple questions. Are we alone? How did we get here? And how does our universe work? But it's really those simple questions that underlie all of the science that we do. And if you want to even pull back further from that, it's really a question of origins and evolution. Where did we come from? Where are we going? But always coming back to that question of are we alone? And again, that question drives the work that we do with assets like the Hubble Space Telescope. Again, looking deeper into space, deeper in time, trying to understand the very origins of the universe, the processes that are taking place. This recent result that came back from a telescope that we're trying to verify from our space-based assets of, did the Big Bang really occur? What does that imply for multiverses? Just absolutely cool science that's going on right now, trying to understand the very origins of the universe. When we study solar systems, there's really been a revolution over the last really 20 years. For many of us in the audience, when we were in school, we had 9 planets. Kids today, I'm sorry to tell you, only have 8, since we lost poor Pluto right off the edge of this slide here. But we always had a notion that this was what solar systems look like, that you had rocky planets close to the sun, gas giants further out, and we developed models to explain why you had an arrangement of planets like this in our own solar system. But then about 20 years ago, we started to develop the technology to detect planets around other stars. And the first types of planets that we could detect were the very largest ones. So we started finding lots of Jupiter-sized bodies. Well, it turns out sometimes those were close to a star. Sometimes they were very far apart. And we realized that our model that we had of how solar systems form, based on our own solar system, was incomplete. And once we had more solar systems, once we had more planets to compare to our own, it's really made us revise our theories, rewrite the textbooks. That's happened in spades this year. All these colored dots, blue and purple, are the planets we had discovered prior to the Kepler Space Telescope. All of the yellow dots are planet candidates that have been discovered by the Kepler Space Telescope over the last several years, over 3,500 planet candidates. Even more importantly, with Kepler's technology, we are now finding planets close to their parent star, but also in the size range of Earth and Neptune. And why is that important? Why are we looking for that? Well, in essence, it goes back to that fundamental "are we alone" question. So when we're looking for planets around other stars, we're looking for planets in something called the habitable zone, the distance from a parent star where liquid water could be stable on the surface. Okay, well, why is liquid water important? We think that liquid water is one of the 3 key ingredients for life. We think you need, based on what we know about how life formed here on Earth, we think you need a source of organics, but that's not that difficult because comets and asteroids have carried organic materials all over our own solar system. So we know those are kind of common out there. We also think you need a source of energy, but that's actually also not that terribly difficult. Many planets have volcanism, which is a potential source of energy. Some planets have lightning, another potential source. But we also think, based on our experience here on Earth, that you need liquid water. And so when we look for planets out in that habitable zone, we're looking for places where we think liquid water could be stable. Well, but let's turn that question around. Let's look at our own solar system. When we start worrying about other solar systems, let's go back to our own solar system and say, where else in this solar system could we have life? And that brings us back to Mars, back to our beautiful Mount Sharp, because we know that Mars has had a long history of having water stable on the surface. And that's certainly one of the results that Curiosity has been confirming, is not just has Mars been an environment where water was stable, but it was stable for a long time. And I would argue that's the 4th ingredient that you really need to get life to evolve, and maybe to get a little more complex, is stability. Life evolved here on Earth. The Earth formed about 4.5 billion years ago. By 3.8 billion years-ish, we had simple microbial type life here on Earth. But to get to something as complex as us took billions of years of a more or less stable environment. So that element of time, stability, is something else we're looking for. And certainly Curiosity has been able to demonstrate that that stable environment took place for some time on Mars. We have other targets in our solar system that we are thinking about getting ready to go explore. Europa, one of the moons of Jupiter, has a thick icy crust. Underneath that icy crust is an ocean, and we recently discovered that there are plumes of that water erupting in geysers from near the south pole of Europa. That process also happens on this moon, which is called Enceladus. It's one of the moons of Saturn. It also has geysers erupting from the surface, and we actually took the Cassini spacecraft, which is a joint NASA-ESA mission, and we flew it through these water plumes quite low, and we measured that there was indeed water coming out of those plumes, but there were also complex organics in those plumes. Now, we don't know exactly what they were. We don't know if they were something like an amino acid. We don't know if they were anything more complex because the mass spectrometer isn't precise enough to be able to tell us that, but we know those organics are there. So Europa and Enceladus certainly are future targets. But in the near term, Mars remains our primary focus. So if we want to get to Mars, how are we going to get there? And certainly there are a lot of things that we can do in this space near the Earth. And Jim's going to be talking about that in a little bit. But certainly right now with the International Space Station, we're doing an awful lot to say what are the steps to get humans to Mars, eventually to search for that evidence of life. The moon remains an extremely important target. People often call the moon a witness plate. All these craters that formed on Mars, the Earth was subjected to that incredibly heavy period of cratering about 3.9 billion years ago. But on the Earth, erosion, water have wiped all signs of that cratering away. The moon preserves our history. So to go back to the moon and study that cratering process helps us understand our own history much better. Other potential targets that humans could visit as we work on the technologies to get ready to go to Mars are the very building blocks of our solar system. Planets are made of comets and asteroids. This is the primordial, the early material that collided to form all the planets in the solar system, and this is sort of the leftover junk. Asteroids are a rich target. They certainly, over the history of the Earth, have produced some of those impact craters on the surface, so there's something that we're keenly interested in, but they also represent a potential target for human exploration. But again, Mars remains our primary focus because of that science question. Did life evolve on the surface of Mars? And I have a bias that it's eventually going to take humans getting down on the surface of Mars doing science to answer that question. We have visited the surface of Mars now over 7 times. From the Curiosity rover to our Opportunity rover to the other images of these were taken by the Viking and the Pathfinder rovers. We have been doing a whole series of science at Mars to answer these fundamental questions about the history of water on Mars, the timing of when liquid water was stable on the surface, and the nature of that environment. Was it really acidic? Was it really basic? Was it suitable for life? And so with the other space nations of the world, we've been on a very conscious path, a science path, of trying to understand the history of Mars. First trying to understand, again, the history of water, then getting into questions of habitability that we've been exploring with Curiosity, and then eventually we're moving into a phase of seeking signs of life. And the first phase of that will be ESA's ExoMars rover, and then NASA's 2020 Mars rover in the future. In the meantime, we have a lot of assets in orbit that are continuing to map the surface to find the targets where there are different types of geologic signatures that tell you about long-term stability. You look for things like clay minerals. Clays form in the presence of water, and we've done that with both our European and American assets at Mars. We have a new mission, MAVEN, that's on its way to Mars. It'll arrive in October, which we're really excited about, and that'll be then followed by ESA's Trace Gas Orbiter. I want to say 2 of the most exciting things for us about Curiosity and then the 2020 rover is these are really the first phase of our joint human science exploration. The Curiosity rover has a radiation instrument on board. It measured the radiation environment between the Earth and Mars. That's critically important because here on Earth we're protected by the Van Allen belts. All of that radiation incoming from the sun goes by us because we're protected by these belts that are produced by the Earth's magnetic field. You get outside of there, any astronauts are going to receive much higher doses of radiation. So the Curiosity rover on its way to Mars and now on the Mars surface has been characterizing that radiation environment. Mars 2020 will continue to do the same thing. Curiosity was and 2020 will be outfitted with all kinds of sensors on the heat shield when it enters into the Martian atmosphere and does that very, very scary 7-minute descent down to the surface through that thin atmosphere on Mars. We're taking all kinds of measurements to better understand that entry, descent, and landing process that on Mars is kind of a scary enterprise. The other thing we're hoping to do with the 2020 rover is actually start on something called in situ resource utilization. Can we use the Martian atmosphere or the Martian surface to actually start mining water or other materials that we might want to use for either rocket fuel to get back off of Mars, or for in situ things like building habitation on Mars. And again, the main aim here is to get geologists, to get astrobiologists, geochemists down on the surface of Mars with a science laboratory on the surface of Mars to do science, to demonstrate and to answer conclusively once and for all, did life evolve on another body? What is the nature of that life? How does it compare here to life on Earth? So we talk about 3 stages. Right now we're working in this Earth-reliant, near-Earth environment with the International Space Station. Then we'll move on to what we call the proving ground, the environment near the moon that Jim will talk about. And then in the meanwhile, while we're working with humans in this vicinity, we will continue our science at the surface of Mars, making the measurements we need to reduce the risk for eventually sending humans to Mars in the time frame of the early 2030s, which is our goal. Now again, we're using the International Space Station for things like a life support system. How do you have a reliable life support system that will last on that 8-month journey to Mars, 8 months back? Health and human performance, huge issues in those areas that we need to beat down the risk on. So the International Space Station is an incredibly valuable platform that the US just extended through 2024. We're excited to have that kind of stability of being able to do research for that 10-year time frame that we have to beat down these risks to get ready for Mars. And again, a lot of them do go back to the human system. When you put a human into microgravity, our cardiovascular system doesn't work the same, our immune system doesn't work the same, we lose bone density, we lose, our muscles start wasting, your intracranial pressure goes up, it puts pressure on your optic nerve, and it's actually caused some peripheral vision damage in astronauts. So, you know, you're getting the picture here. Zero gravity isn't necessarily the best environment for humans. But we want to go to Mars, and so we're going to have to find ways to mitigate those effects, to make it so that when we get astronauts to Mars, they can get out of the spacecraft, they can start working on the surface of Mars. So we've listed all the risks, which also include, you know, proper nutrition, isolation, along with the health risks. And we have a plan on how to reduce each of those risks to be ready to send humans to Mars in the 2030s. And this is exciting for us at NASA because we've really brought all the different pieces of NASA together to work together, from the science group to the group that normally focuses on human exploration in the ISS, to the technology piece, which Jim is going to talk about in a minute, really working together towards this common goal, which is, again, not just NASA's goal, but an international goal of trying to get humans to Mars by the 2030s. So Jim is going to give the second part, and then we will be happy to take questions.
Awesome. Testing 1, 2. Am I on? Great. So Ellen did a great job of telling you about the science of where NASA's been and where we expect to be going and how it can support human exploration deeper into space. And like any institution, as NASA's grown up, we have created these 3 areas, if you will, that have kind of looked out for themselves. You know, science has been looking out for science, and technology's been looking out for technology, and the human exploration guys and the astronauts in orbit, they're always looking out for themselves. In fact, I'll tell you a quick story. I'm full of stories. In fact, I may not even get the talk done. I just tell you stories. When I first came to NASA, what drew me to NASA was to work on something called the Space Station Freedom. It was one of the first incarnations of what is now the International Space Station. And one of my jobs was to help integrate the robotics into the Space Station Freedom. And there was this huge debate over the handholds that the astronauts and the robots would use. Would a robot be allowed to use the handhold that it was designed for an astronaut? Would an astronaut be able to go out and replace a unit that was designed to be replaced by a robot? And they kind of arrived on a sort of a separate but equal approach. You know, that was in large part because of our culture of like separate but equal, kinds of things. And in fact, today, what's happened now, that was 25 years ago. Today, what has happened is NASA has adopted a strategy that says we will design our robots to meet the mission. And if you look at our humanoid robots today, they're designed around features to support humans in the way that they're designed for humans. So we're making our robots today function with 5 fingers, with vision binocular separation in the right way, and that sort of thing, so that we're adapting the technology to meet the human world and basically creating that crossover. And that's really what we're trying to do within our agency, is create a crossover between science and exploration and technology to enable the broader vision. The broader vision is that as a globe, we will move off the toehold that we have in space right now. The toehold is the International Space Station. It's a permanent presence, but people come and go 6 months at a time. Hopefully someday we'll extend that to a year. But right now we have this toehold in space, and we don't want to let go of it. The next destination for NASA, thinking further out, is Mars. And so it's going to take not only the joining of all these efforts within NASA to be able to accomplish that, but also the joining of the efforts around the globe to be able to accomplish it. And we can talk a little bit more about that maybe during Q&A about how we're cooperating. One of the things that we'll be doing as we get to Mars, we'll be running test cases. We'll be playing in the space between the Earth and Mars. In this particular case, it happens to be in orbit around the moon. What we're going to do is we need an object. We first thought, well, we'll send an astronaut to an asteroid. That would be good. And then we realized how hard that was. It's just trying to catch up to one requires so much delta V, rocket propulsion, that it was almost impossible for us to be able to send humans to an asteroid. There are plenty of them. There's 1 or 2 a month that zing between the Earth and the moon. But catching up to it is really hard. And so we decided what we would do is we would redirect one. So there's a bold plan for you. And that's what this talk is about. So in order to find one to redirect, we had to identify it first. And I'll tell you, of the hundreds of thousands of asteroids that we've found so far, there's one, right? So we're going to continue to look. And we've engaged the international community in looking for appropriate asteroids that we could send humans to. And along the way, as we do that, we do great science. We're refining the technology, and we're helping to protect the planet. Because as we find asteroids that are that close to Earth, we begin to understand and characterize the threat from asteroids. That's called planetary defense. And so we've actually started an international engagement around planetary defense and the Near-Earth Object Program, observation program. And most recently, we've been working with South Africa. In fact, I was asked to give a shout out to South Africa. The Royal Observatory, the oldest observatory in Africa, established by the British so that you could navigate around the Cape there, is one of the premier places in Africa to go to have astronomers help us look for asteroids. And so we're engaging with them. And as part of that initiative, we're helping to support the education of certain people groups within Africa. And so we've been out to what they call a Sci-Fest. And so I'm supposed to say hi to all the Sci-Fest kids, 50,000 of them. In South Africa. And that's what we're doing. We're trying to identify the right asteroids. Then what we'll do, once we've found the right one, we'll bring to bear all the technology that we've got. And we'll snag it. In one case, we'll bag it. And then we'll drag it over into orbit around the moon. And then, once that's in orbit around the moon, then we can send humans to a target that would enable us to operate in cislunar space, that space between the Earth and the Moon, that would allow us to practice deep space operations without having to go the full 8 months all the way out to Mars and then come back. And so that's the plan at the moment with the Asteroid redirect mission. Just a quick concept there. We're looking for about a 10-meter asteroid. 10-meter asteroid is not a very big one. You know, it would fill this room for sure, right? But if it were to come in over the Earth's atmosphere, we might not even notice it. You know, it wouldn't make too much of a big deal. Maybe pebbles might make it to the surface of the Earth. So it's not a very big one. But it requires a lot of interesting technology. And one of the concepts that we've got is to create this giant bag that's roughly 20 meters across and wrap it up and then slowly cinch yourself down onto the surface of this asteroid. Now, the difficulty in all that is you have to do that while the asteroid is spinning, because most of the things in our solar system spin. The asteroid that we'll find will probably spin as well. And so we're going to have to get ourselves tightened up against that asteroid and then stabilize it and then push it just enough so that it gets into the orbit around the Moon, into a retrograde orbit that we can then send astronauts to crawl over the surface, open up the bag, collect the correct samples, do the kinds of operations that you would do in orbit around Mars maybe, and as well as live and work in a space for months as they explore this asteroid that we've captured. The point isn't really the asteroid. The point is the living and working and the technology to be able to do that around an asteroid. And so, I mentioned the three features that were coming together. The top line is the science program that's going to help us find the asteroid. And we've doubled their program budget. So if you're an astronomer and you want to start looking for asteroids, you might want to start thinking about helping us out in that area. We've made great strides in finding all of the asteroids that are a kilometer or greater. We found 97% of them or something like that. But there's so very few of them that they're not, and a kilometer is too big for us to push around. So we're looking for something on the order of 10 meters, and we estimate there's something like 1.1 million of those out there somewhere. We just need to find the right one. That's run by our Science Mission Directorate. The Asteroid Redirect mission is largely a robotic technology effort in which we use very high power solar arrays, a solar electric propulsion that is an ion propulsion engine that will ionize xenon and spew it out a rocket nozzle so that we can push this asteroid that we've collected into the correct orbit. We need to be able to figure out how to rendezvous with an uncooperative object that is of that mass and size. And then we will have to push it. And that's going to be quite a feat. The Dawn mission, I don't know if you've heard of the Dawn mission, is also an international mission that we are moving. We launched it in 2007, and we went out to the asteroid Vesta using an ion propulsion system. And then after we explored Vesta, we're moving it on to Ceres, which is the largest asteroid in the asteroid belt, now classified along with Pluto as a dwarf planet. And it's using the ion propulsion system to get there. So this is a very efficient system. It allows us to visit 2 different destinations at one time. 450 kilograms of xenon is the fuel. To move this asteroid, we expect that we're going to need something on the order of 12 tons. So from less than half a ton to 12 tons of xenon. Just the technology in the storage tank alone is a huge challenge. So this is a really big deal, and we're going to bring to bear all of NASA's innovative thinking and technology in order to be able to grab this asteroid and drag it into orbit around the Moon. In the meantime, the Human Exploration and Operations Mission Directorate, which is where the astronauts live or are funded out of, they're working on a new rocket and a new capsule rocket ship that will enable them to live in space, in deep space, much longer than they have been able to before. And that's called MPCV, or Orion for short, and the SLS, the Space Launch System. And in that time frame, in the 2020 time frame, it should be ready to go rendezvous with the asteroid that this mission grabbed that was found by this science effort. Long way of getting to that story, I guess. And this is sort of just a collage of what would happen. We would, once the asteroid was captured and in the correct orbit, we'd launch the astronauts Apollo style on something called the SLS, which will have its maiden voyage in 2017. It's the largest rocket in the world, except for the Saturn V. So it's an enormous rocket. The crew capsule and quarters will move on out towards the moon. It'll rendezvous with the asteroid that's been bagged and captured by the robotic asteroid redirect mission. There you can see it's rendezvousing with the robotic mission. There's supposed to be humans inside there. And then once they've sampled it, they'll return Apollo style back to Earth along with the samples. And then those samples will go into NASA's collection at the Johnson Space Center and made available to researchers around the world. Some of the technologies, I've already kind of mentioned these, are our extravehicular activity technologies like suits. New spacesuits are going to be required. Tools for getting around these sorts of surfaces and being able to harvest samples on a target that you really don't know that much about are going to be required. And that the protocols for humans to live and operate in space for long periods of time are going to be required. Crew transportation, deep space rendezvous, we've talked a little bit about that. How do you rendezvous with an uncooperative target? That's very important. Solar rays, getting the kind of power that we need in order to be able to create the propulsion system that we need. That's a challenge that we're already working on, as well as the propulsion itself, the in-space propulsion. And it's a challenge just to go from the Dawn kind of system to a system like this that could move a rock that is that big. So that's the vision. Mars in 2035. It's 20 years away. Many of you sitting in this room, some of the younger faces, you could be this astronaut. You could be part of the team that is this astronaut. It's a global team that's going to send those boots to Mars. And that's one of the things I want you to think about. It isn't about a stovepiped, one group's thoughts on how you get to Mars. This is a global thing. It's going to require all of us coming together, just like we're trying to marry technology and science and human exploration in order to accomplish one bold, audacious goal. And with that, I think we'll take questions.
So there's about 40 or so minutes for questions, so keep them coming. I really want to ask one first, if that's okay with you guys. Can I go, please?
Can you go?
Can I go? Can I sign up?
Sure, go right ahead.
Can we do that? Is that how it works?
How many people in the room would say that if they could go to Mars, they would volunteer? I'm curious how many people would go.
Awesome.
Awesome. Okay.
Yeah.
All right.
Okay, well, serious question. How do some of these young people start to get onto that path for 20 years' time where they might be in that excellent suit?
You know, the first thing they need to do, which is something that is a priority all around the world, is really think about science, technology, education, and mathematics. Those subjects in school, while sometimes they're a bit of a trial, are something that are really important, not just for being an astronaut, not just for working on technology, but they're really important for so many subjects, from whether you want to be a banker or whether you want to be a doctor or whatever your career is. Really making sure you get a solid foundation in mathematics and physics is really critical. And so from the beginning, and I've had a kid ask me, you know, how do you get cargo from the ground up to the International Space Station? How do you guys do that? And I looked, this was at a school I was visiting a couple months ago, and I looked at the child and I said, oh, I'm so sorry, you're going to really hate this answer. It's math.
You do it with math.
We do so much with math.
I would also say determination, right? You have to decide you want to do it. I mean, you're sitting there with the rover design. I'll tell you a story about the wheels on that if you want. I was not the best student in the world, right? In fact, I was lucky to get out of college. This is true. This is true. And what happened was I just found something I was good at, and I just stuck at it. I kept on going, and I kept doing what I loved. And so find what you love and do it really well, right? And over time, you'll be able to come to work for NASA. You know, I mean...
Or ESA.
Or ESA.
Or the UK Space Agency.
Or the UK Space... That's a good point. You know, it is a global thing. You can do all those sorts of things if you just decide what it is that you love to do and then just go do it.
All right, so it's as easy as that.
It's just that easy. Just sign up.
A bit of maths. Come on then, let's have your questions. Let's get your hands up. I'll take two at a time, maybe.
Two at a time.
You over there in the corner, and then you there as well, in the same row.
First of all, thank you very much indeed for a fascinating presentation by both of you. I was recently reading I believe it's still an unpublished article by a Russian scientist talking about going to Mars and saying that in fact, as far as he's concerned, the main thing should be not to work out a mission which would go to Mars, do some work there and come back, but go to Mars and stay there.
Right.
Are you looking at that? That's my first point. Second, very quick one. Given what's going on in politics at the moment, and given that the Russians are saying, well, if you're going to carry on not being nasty to us, we're not going to let you use our rockets, does that worry you?
Well, for the first part, certainly we feel that we have actually changed how we start talking. You know, we've always talked about our Mars exploration program, and you saw that in my slides. We're actually trying to change our terminology, which I think was a great idea by the guy, Bill Gerstenmaier, who heads our Human Exploration Directorate. We now talk about pioneering Mars. So when we send humans to Mars, when we make this big international effort, I think humans are going to Mars to stay. Now, I don't think that first group of humans will necessarily stay there for the rest of their lives and not come back. But I think we really want to look at this as the beginnings of establishing a human international outpost on the surface of Mars. I don't really think it's fair to ask of anybody, you're going somewhere and there's no chance of you coming back. That's not NASA's intention. We certainly want to say we want to go to Mars. We want to have it be possible for those people to come back if they want to. But I think it's the beginning of a sustained human presence on Mars, which I think is really exciting. For the second part, we have had a rich and wonderful relationship with the Russians on the International Space Station. It's been an amazing partnership, not just with the Russians, but with the Japanese, with the Europeans. We would not have the International Space Station we have without international cooperation. And NASA has received no official notification that relationship has in any way changed. 2 nights ago, we landed 2 astronauts back from the International Space Station in Russia. And so on a working basis, a day-to-day basis, that relationship continues.
Yeah, and I think long-term it requires vision, you know? And if the vision is strong enough, if the intention of the people is strong enough, then it'll overcome these momentary blips in global politics, you know? And we've seen that time and again in various relationships. So I'm with Ellen, you know, we're still working with the Russians, and we certainly hope that we can continue that partnership.
Okay, how about you?
I've got a question about asteroids.
I'm sorry,
What
where is he?
If
Oh.
we are trying to catch bigger asteroids, which are not 10 meters, how are we going to catch them then? Still by bags?
So that's a really good question. The real question is, why would you want to catch one that big? And the reason you might want to catch it is because you might want to nudge it out of the way, because if you're looking at it carefully enough, it might actually, you might be able to project its trajectory and say, 20, 30 years from now, it would come too close to the Earth. It actually might hit the Earth. In fact, a while back there was this asteroid that we thought, it was called Apophis, that we know cycles around on a roughly 13-year cycle, and we thought it might actually hit the Earth. And we watched it and we watched it, and for a while it looked like it was going to hit the Earth in the 2030s or so. But in fact, as we watched it even more and we took data on it, the error in our estimate started to reduce, and we began to realize that no, it's not really going to hit the Earth. However, there have been many asteroids that do hit the Earth. In fact, some hit the Earth routinely and we just never even know it because the atmosphere protects us. The bigger ones that could cause catastrophic damage, like the one that is attributed to wiping out the dinosaurs, are on the order of 1 kilometer or larger. And if we ever found one, we would want to know about it many, many years in advance. It's not like it's just going to appear out of nowhere. They're big enough that we can see. Like I mentioned earlier, we think we found 97% of them. And so what we would need to do is to understand what that asteroid is made of, how it's constructed, so that then we could go and just nudge it just a little bit. And if you nudge it just a little bit over the period of 30 years or so, you can move it out of the way of the path of the Earth. You don't have to move it very much. And so that's the challenge with the larger asteroids, is just to move them just a little bit. And there are a number of ways you could do that. You could go and attach a big rocket engine and try and push it, right? But they're pretty big and they're pretty massive. And that would be about like you going down to the pier and pushing on a cargo ship, you know? So there's also this idea that maybe you could blow it up. Well, maybe that might even make your problems worse. You don't know. There are some ideas that you could go and if you could change the mass of it by maybe landing something very heavy on it or putting something in orbit that's very heavy. You change the mass, and then as it progresses in its orbit around the solar system, it will change its orbit as well because of the conservation of angular momentum. And so ultimately, if you do it right, it would miss the Earth. There's another really cool idea that says, as this thing rotates, it sees sunlight on this side, it warms up, and then it cools off as it rotates around. That warm spot cools off, and another spot warms up. And so you get a little bit of push. It's tiny, very, very tiny, but you can measure it. A little bit of push because of that warming and cooling. The radiation of the heat gives it just a little bit of push. Well, if you could enhance that by maybe painting one side of the asteroid white, there are some theories that maybe you could do that. And the asteroid over time would just push itself out of the way. So there are lots of things that people are thinking about, physicists and dreamers that are thinking about ways that you could move an asteroid out of the way. Maybe you could help us with that.
And I've got a second question.
Oh boy. That one was hard enough.
What is the chance of mislanding rather than hitting the side of the capsule on the asteroid rather than the bottom of it? Because, I mean, it's only 10 meters, and compare it with other things, it's quite small.
It is quite small. So the challenge is if you've got these two things floating in space, and one is massive and it's spinning, and the other thing is inertially stable, how do you match the speed of it just right so that you can pick a spot and land on it, right? And you do that from way far away, right? Because it's robotic. There aren't humans right there in the moment. So you have to figure out how to do that just exactly right so that when you touch down, it doesn't drag underneath you and tear off your solar arrays or damage the clamps. In fact, the European Space Agency is going to land on a comet in October of this year. And that would be something to watch because they've got this probe. A mission called Rosetta will drop a probe onto a comet. It would be awesome. And when I was there the last time, they had these little hooks because they were worried about that they would bounce off, if they touched down, because there wouldn't be enough gravity to hold them down. They would actually clamp themselves onto the comet.
Okay, so. Thank you. Let's go to this side. I think it'd be good to get some more. So one there, and then the chap in the green. Jim, you forgot to mention the documentary that was out several years ago where Bruce Willis landed on an asteroid.
Yeah, that's right. We could send Bruce Willis. That's the other thing.
Two titanium space shuttles. I think that's also a possibility. Just think about that.
Simultaneous launches.
That's right.
Yeah.
Over there.
What research at NASA is being done at the moment to completely autonomize path planning systems for your Mars vehicles, especially as rovers like the Curiosity rover have a limited lifetime and move quite inefficiently?
It's a very specific question.
You want me to answer that?
Yeah. That's not my field. I'm a geologist.
So we are investing several $1 million a year in looking at autonomous systems and the intelligence necessary to allow robots to move on their own, right? You remember Spirit and Opportunity. Spirit died, right? But Opportunity is still moving, and so we're using that even now as a opportunity to test out some autonomous driving software. But it's mostly designed to protect the rover itself. It's designed to assure that it doesn't drive into a ditch or something like that. And the reason is because of the time delay. There are humans that are watching this thing. They call them rover drivers. They actually have little licenses. And the rover drivers, they're controlling this rover, but it's not like controlling a toy car. There's sometimes as much as a 14-minute delay between the time the driver says go that way and the time the rover actually does it. So there's a lot of path planning that has to be done by humans. And then the autonomy system kicks in and helps to execute it. That's where we're at now. We're not at the point today where we could say, you see Mount Sharp, I want you to climb it, right? We're not there yet. You mentioned that the rover was limited lifetime. I'll just point out that Spirit and Opportunity, Spirit lasted 7 years. It was designed for 90 days, right? Opportunity is still going, right? And I think it's working on its 9th year now, right? So in order to design things that will withstand the rigors of the environment, we often build in a lot of margin. Right? And so Opportunity is reaping the benefit of that. And I have every expectation that Curiosity will as well. It's designed by the same design team, and it's nuclear powered. It's not going to have the same problems that Spirit and Opportunity did with dust getting on the solar rays. So I think it's going to be a rover that will be there for a long time.
But that very inefficiency is really why, in the end, I think it's important to send humans there, because the rovers are inefficient. We're working on more and more autonomous technologies, but the fact remains that a human can do so much more than a robot can in such a smaller amount of time. And ultimately, that's why I think we need humans down on the surface.
So yeah, the principal investigator, Steve Squires, of the two Spirit and Opportunity rovers, has said that all of the science that was done by one of the rovers in the 7 years-ish that they've been there could have been done in a week if you had had a human on the surface. And the large reason that the rovers move so slowly is because of that time delay, the time lag. So.
Okay. There's a question here, two ahead. Chap in the green. Yeah, thank you.
I want to ask about propulsion at the far end of the time frame of getting humans outside the Earth-Moon system to Mars. Back in the 60s and 70s, there was NOVA Project Rover, which developed nuclear thermal engines. So that better ISP, better specific impulse than chemical engine, not anywhere close to ion engines or even Vasimir. But that would let you get to Mars much faster, which means less radiation exposure, and essentially easier to keep people alive at that time. Is there any thought of putting a nuclear upper stage onto the SLS? Of getting NOVA back up to speed from where it's going?
So in fact, there is. The answer is yes. We're working on advanced technologies that will make nuclear thermal propulsion a reality, and for the exact reason that you said.
Jim, would you mind just explaining what the difference is between these different types of propulsion
Okay.
for the rest of us?
So NERVA was a project that was canceled before I even got out of high school. So That was some time ago. But nuclear thermal propulsion takes a fuel, usually either hydrogen or oxygen, and runs it through the core of a fission reactor, heats it up, superheats it, and thrusts it out a rocket engine, right? And that creates a really efficient, as he said, thrust, right? Which, if you had the system in order to be able to do that, would enable humans to get to Mars in much shorter period of time than the 8 months that it takes. An ion propulsion system, actually, what it does is it takes xenon, or a noble gas, and strips off an electron to create an ion, accelerates it through a grid, and then pushes it out a rocket engine. And what happens there is you get a low amount of thrust very efficiently, but you can do it, you can thrust continuously. And that's how Dawn got to Vesta, was just constantly thrusted. So one person that I know refers to that as the power of patience, right? So that's the difference. And for sending cargo to Mars, an ion propulsion system might actually be the ticket, because there's no humans on board. You could design the thing to withstand the rigors of a long journey through space. For humans, you really want to get them there quickly, right? And so the idea of a nuclear thermal propulsion system, a fission reactor that we would then blow, I think it's hydrogen through, is in works. In fact, there have been simulators set up at Marshall Space Flight Center, and there's a technology down select on how the cores will look that will be made this fall. So they're trying to decide whether to use a ceramic or a carbon set of cores. And they're doing the trades on that now.
Instead of spending so much money on catching an asteroid to orbit around the moon, could you not just put into an orbit a piece of rock that's about the same size from Earth?
No. If you think about how hard it is to get out, just to get a small group of astronauts out of the Earth's gravity well, it would be very difficult to do that. However, thinking innovatively, it is possible that we might consider going to some other asteroid much larger and grab a boulder off of that and bring it back and use that as the destination, the practice ground, proving ground for the astronauts. It's a good question. See, I think you had told him he
Yeah, absolutely. Yeah. So, yeah, if he comes to the front, and then someone else on this side. Okay, we'll go to you straight afterwards.
How useful would Lego be to get to Mars?
How useful would Lego be to get to Mars?
Oh.
What do you think?
You know, everything that we do at NASA, someone has to imagine first. Someone has to think it up creatively. And that's why, to some extent, the arts are such an important part of education, because you have to learn to be creative. You have to learn to be innovative. We're trying to do really hard things. Trying to get humans down onto the surface of Mars is a good thing. So being able to play with concepts, is a cinch really going to work, or should we try something out? So building models, testing things on a small scale before we ever spend the money to enlarge them up to a big scale is really important.
And I'll add that NASA has an agreement with LEGO as a partner. We've sent Legos into space, and astronauts have put them together in space. And along the same lines, we use the notion of Legos because it engages people's curiosity and innovation to inspire kids to come out to NASA events and think about what they can do in the the
So does Lego behave differently in space? Do we know? Is that
They're still really hard to get apart once you get them together.
All right, this question here. Let's go, and then we'll go straight to just behind you.
I know this is a relatively simple question, but how much evidence is there of like intelligent life on Mars? Because there's all the photos on the internet, but you can't really trust it.
No, you definitely can't trust it. When you think about it, again, life here on Earth evolved about 3.8 billion years ago after the Earth formed 4.5 billion years ago. It stayed in relatively simple forms for billions of years until we got to something as complex as us. That stable sort of environment never persisted on Mars for that length of time. So the chance of there being intelligent life on Mars is fairly low because Mars just lacked that huge stability of environment that we had here on Earth. So we anticipate, based on the science that we know from understanding life here on Earth, that any kind of life forms on Mars would in general probably be relatively simple. So single cell, multi-cell, not anything cool. So, on the other hand, if you want to think more exotically, you would think of a place like the European Ocean, where you have that thick icy crust with the ocean underneath and probably volcanoes at the base of that ocean. That might be a place where you could start saying, all right, maybe that environment has been stable for hundreds of millions of years, maybe for 1 billion years. So that's where you can start thinking that stability of environment may persist, where you could start asking that kind of question.
Ellen,
Yeah, don't trust anything you see on the
wanted to
internet.
follow up on that. There's lots of evidence that liquid water was there on the surface of Mars at some point in its history. We see a lot of evidence for that. But do you think there is any now, somewhere, underneath the ice caps, maybe somewhere around places we've not been?
I think under the surface of Mars, there are places where you can get, at times of the day, times of the season, where the temperatures actually creep up around towards freezing. And so it is potentially possible. So one of the things that we would love to do at some point is be able to drill down, because outside of that radiation that affects the surface of Mars, in a more protected place, there could actually be living life, not just evidence of past life. When we're looking on the surface, we're looking for evidence of past life. But if we could get down below that harsh radiation at the surface, we could potentially look for extant life.
Hi. Just a question came to me when you were talking about Europa. I noticed you used the same font as in the title cards of 2001. So I was wondering...
That's very specific.
Yeah, there's a factoid for you.
I was wondering, or not there, but earlier in the slides, but I was wondering, once people have gone to Mars, is it like a completely other sort of issue to go as far as Europa, or is there a feeling that, once you've done one planet, you could, use the same technology, just kind of multiply it, few 100 million miles or whatever?
I would definitely dream of the day when we can go beyond Mars. Certainly on Mars, it's a place where you can think, all right, we can establish a permanent human presence. We can live on Mars. We can have scientific careers on Mars because it has such a relatively benign environment compared to other places. Humans on Europa is a pretty tough one, and that's because of Jupiter. Jupiter produces an awful lot of radiation that makes it really hard for us to even put a spacecraft in orbit around Europa. The current concepts for Europa missions we're looking at are actually missions that go into Jupiter orbit, so that at times we can get the spacecraft out of that horrible radiation environment right near Jupiter where Europa sits. I have a personal bias that I would dream about one day seeing humans go to Titan. Titan's one of Saturn's moons. It's actually the only other place in the solar system where it rains. There are seas on Titan. Those seas and that rain is not liquid water. They have a complete hydrologic-like cycle, but the working fluid is methane and ethane instead of water. Totally fascinating place. A little chilly, about 94 degrees Kelvin on the surface, but putting that aside, it has a nitrogen atmosphere. Fascinating place, would be a cool place to go at some point in the future.
Could you have different types of life living there to us?
That's a hugely intriguing question that I particularly love. When you go back to my story about the solar system and how our view and models of the solar system changed when we had other solar systems to compare and found, okay, not everything is like us. Now let's go back to that story of life, where I said you need liquid water, that's the story of how life evolved on Earth. Okay, what if life is different in different places in the solar system? Do you need liquid water? Could that liquid methane and ethane on Titan, even in those very cold temperatures, could that serve as a basis where life could evolve. We know there's tons of organics on Titan. So Titan to me is a fascinating place to go analyze what is in those seas on Titan, because it pushes that question: what are the limits to life? Does it have to be a carbon-based form? And again, so many of our notions are based on what we know about Earth, and that's the proper scientific thing to be doing. You build on what you know. But places like Titan, I think, really push the envelope of how we think, and would be fascinating to go and analyze.
Fantastic. How about we stay back there, you in the blue there.
Hello. I was just wondering if you could summarise the main challenges, in terms of work streams. You've talked about human physiology and you've talked about propulsion. What are the other major challenges?
Well, I think I'll answer, and then Jim can answer. I think really, to me, the two tallest tent poles in the very big tent of Mars human exploration challenges. One is definitely the radiation question. How do we protect humans on that 7 or 8 month trip to Mars when they're going to be subjected to cosmic and solar radiation? And the second one is entry, descent, and landing. You're going, I think, 17,000 kilometers a second? When you get to the top of the Mars atmosphere, you have to slow down to 0 in 7 minutes. That's really, really hard. Okay, now we're talking 40 times as much mass with people on board. We don't know how to do that yet. We don't know how to slow ourselves down that fast. We really, this is a big challenge. And so you might hear of a company or a group coming forward and saying, oh, NASA should do this in the 2020s. Why are they waiting so long? We want to make sure we get living astronauts, healthy astronauts, down onto the surface of the Mars. That's kind of a non-negotiable point. And we feel like we have a lot of work to do, a lot of investment to make. And again, that's what takes it from being a NASA problem to an international problem, because we can't do this on our own. We need all the space agencies of the world working together.
So the other thing that I would add, entry, descent, and landing is hugely important. Seriously, the rocket to get off the surface of the Earth is hugely important. Environmental control and life support.
Yeah.
A lot of what we do on the International Space Station today, we kind of scoffed at the Russians when they first came up, and we went and visited Mir, and we saw how much maintenance they were doing. We're doing maintenance all the time on the International Space Station now. If we're going to send a small crew to Mars, we need to have reliable systems that will keep our astronauts alive without requiring a great deal of maintenance. And so we're working on that today, and some innovative things that that you might not think of, like using biology to help us scrub the atmosphere and the wastewater. Those sorts of things are being worked on at our Johnson Space Center. Optical communications, higher bandwidth communications, I think are going to be extremely important. We're in a bandwidth gluttony here on Earth. And if we want to go with those astronauts, we're going to be expecting high-definition video back. The astronauts are going to want to be able to phone home. And even though we won't be able to solve the latency problem, we will still be able to send massive amounts of data back, which is really the primary reason for going from a scientific perspective. So an optical communication system from Mars. I don't know if you know this or not, but we just flew a mission, we just terminated it, called LADDI, that flew the first laser communication system from the moon. And we communicated back from the moon at 680 megabits per second, which is huge. That's hugely fast, right? But from the moon to the Earth is a fairly small distance, right? And so if you get a little bit of wobble in the spacecraft, then the spot on the Earth will move around a little bit like this, and the receiver that's in the middle of the spot will be able to continue to hold lock on the signal. The same sort of system at Mars, when it broadcasts from Mars back to the Earth and you get a little bit of vibration, the spot size will move more than the Earth's diameter. So one of the biggest challenges in optical communication isn't the optics at all, but really the stabilization systems. And and what happens to the communication when the astronaut's leaning up against the side and he sneezes or something? So,
Okay. Let's go to this side, shall we? How about you here in the stripy, but then behind? Yeah, in the stripes, and then we'll go backwards. Or the other way around, doesn't matter.
Hi. Sorry. If you're considering the future and the long-term habitation of humans on Mars, is it ethical to consider reproduction and how the radiation and difference in gravity affects developing embryos and stuff?
That's certainly something that eventually, if you say people are going to go and live there for long term, it's certainly something we're considering. People will volunteer, but is that necessarily ethical? And so we struggle with these issues, and that's why it's important for us to really try to quantify the risk and then mitigate the risk to a point where you say, I can ethically ask someone to go do this. So then when you think, okay, what are the longer term implications for things like reproduction and if people are eventually living on Mars, we're going to definitely have to cross that bridge at some point. We haven't gotten there yet, but we will.
You have to find roles for all the children as well. Kind of stuck, wouldn't they?
Yeah, no, they would be kind of stuck. I think it's fascinating. It's so fun. It's so fun to go from this mindset of saying, I'm exploring a planet to saying I'm pioneering a planet. And in that sense, you do have to take on more risk. You do have to have a different risk posture. And risk is obviously something we really are concerned about at NASA. We think about all the time. But when you say, okay, would you not have gone to America, to explore? Would you not have gone to all the exploration we've done over the years, whether it was to Antarctica or the Arctic or you have a different mindset when you're a pioneer maybe than you do when you're an explorer. But again, our primary concern is getting their people safely and giving them the option of coming home if they want to.
Okay, just two behind you. Yeah.
No, when humans would say land on Mars and thinking about setting up a form of base, what sort of machines and pieces of technology would they need to set up to be able to live properly?
Well, that's an interesting question. It really depends on your perspective. So we have a number of groups of engineers that get together and work on the various architectures for a particular, what we call design reference mission, right? And as we've developed these missions, then we can begin to look for common bits of technology and facilities that would be necessary on the surface of Mars. So we are at design reference mission 5, I believe, so there have been 4 before that. And generally, what we're looking at is starting with some sort of modular power system. They're thinking they're going to need something like on the order of 40 to 70 kilowatts of power continuously in order to support humans on the surface of Mars. And so we're looking at if we're going to have to create a space-based nuclear reactor in the first place to get them there, that possibly we could create a nuclear-powered electric system that we land on the surface of Mars to supply power. Then it's a question of habitation. Where do you put the habitation, and what does that look like? And there are some folks out there with innovative ideas, and maybe someday you'll come up with one too, where you could inflate a habitat. And so you could take it shrunk down, and then when it gets down to the surface, it kind of opens up. That's an idea. Another idea is to find a lava tube that's caved in and then inhabit the cave underneath so that you're protected from the solar radiation and maybe create some stability temperature-wise. Beyond that, then we're expecting that there'll be an array of robotic craft that might be moving dirt or might be helping with construction of other facilities, those sorts of things. We would probably go exploring using locally controlled rovers instead of rovers that are controlled from back at Earth, and that would allow us to explore very much faster. So there's lots of things that could be considered. There are even concepts for airplanes that would fly, wouldn't carry human beings, at least not yet. But the idea would be there would be airplanes that would fly and characterize the atmosphere of Mars for us. So those are the sorts of things.
Ellen, can I ask just on that one as well? You've got all this stuff there. You've got them there safely. What is the typical day of an astronaut there? What are they going to be doing? And how hard is it to work there? Are we talking 10-hour days? Are we talking they can only work for an hour before they get too exhausted? What would it be like?
You know, I'd go back to the days that our astronauts are having right now on the International Space Station, and I think the days on Mars would be relatively similar, fortunately or unfortunately. The astronauts have to spend a significant part of their day exercising to help with that muscle wasting and bone density loss. We found that just like here on Earth, if you want to stay healthy, you need a healthy diet and lots of exercise. So some part of their day would have to be devoted to that. Medical testing, every day we require the astronauts to do some degree of medical testing just so that we can be monitoring their overall state of health, obviously a really critical issue. They spend, as Jim said, a significant part of their days on the International Space Station working on maintenance, and I think to say that anything on the surface of Mars to be any different would probably be unlikely, whether it's, you know, some pesky piece of equipment that's not working quite right. So I think you'd get down to it and probably have about half of a day, maybe 4 or 5 hours to actually get out there and collect samples, do any kind of science. They're also going to have to, we've talked about greenhouse structures, they're going to have to be spending part of their day producing their food. We're doing a lettuce experiment right now on the International Space Station where we've sent lettuce up to be growing so that the astronauts can eat it. They're going to have to find ways to have sustainable food. So a lot of their day is going to be taken up with kind of the how do I live on Mars kind of tasks, and then part of their day will be able to be science.
Okay. Let's have some more questions. Let's stay at the back a bit further. Yeah, you sir. And then if you can
hi there. I just wanted to ask you, talked a lot about landing humans on asteroids as a kind of practice ground for going back to Mars. And I wanted to ask whether you're considering sending humans back to the moon for the same reason.
Okay, hold your thoughts. Back to the moon, and then final question there. And then we can choose whichever you like to answer. I'm sure one of you can do it.
How can you reliably test machines that you're going to put on Mars as it's not the same conditions on Earth?
Okay, 2 very good questions. Yeah, now your final ones.
That's a great question. You know, we have learned absolutely so much from the Apollo program about landing on the moon, about operating on the moon. Mars is a very different bear. With that high speed that you reach Mars at, it's not comparable. We can go into lunar orbit and slow down to basically 0 and just kind of plop onto the surface. It's much lower gravity, no atmosphere. Mars, you reach at a really rapid velocity. You have to slow yourself way down, big gravity compared to the moon, atmosphere. So entry, descent, and landing, again, this huge, tall tent pole. Landing on the moon just it really isn't comparable. So NASA has decided, rather than putting our assets into landing on the moon, we would rather operate in that region near the moon, practicing those technologies we need for that 8-month journey when the astronauts are in a vehicle, not on the surface, because we feel that's the critical portion that we really need to test out. Many of our international partners are interested in potentially going down to the surface of the moon to test other technologies, and we're anxious to work with them if they're doing that. But we want to put our assets, and again, this is why that international roadmap that we're working on is so important. So how do you split up all of these technological challenges among the nations of the world so that every country is making technology investments in their country, which help their country's economies in the long run, help give them a piece of the pie, so to speak. And so we've decided to focus on the Mars-related technologies and leave lunar landing to maybe somebody else.
First, I'll say every bit of technology that NASA sends into space is tested in a relative environment on Earth. College students putting a small satellite in space, they're not managing the same risk as we are. So there are huge vacuum chambers where we simulate the vacuum of space. Those vacuum chambers oftentimes have cryogen-cooled liquid oxygen, liquid nitrogen cooled shrouds that help us simulate the warmth and the cold of space. There are vibration tables that we mount everything on, and we shake the daylights out of it to simulate the rigors of the launch. And then there are long-term tests that we run things through as appropriate to demonstrate that they'll last the lifetime that we want. And that's how we try and make sure that everything is going to be all right with the technology.
Can I just ask you to put your hands together one more time for Ellen and for Jim? Thank you very much.